Okay. It's on this one here, so just try it.
Okay, great, thanks. Thanks a lot.
It's a great pleasure to welcome Saheli Sarkar, who is going to tell us about quantum criticality on a compressible lattice. An intriguing title.
Indeed. Let's see.
Thanks for great to give this in now.
Okay. Thank you very much, Ranjo, for giving me this opportunity to be able to present my work. Well, good afternoon, everyone, and of course the audience over Zoom. So currently, I'm a postdoc in condensed matter physics and material science division, Brookhaven National Laboratory, and today I will talk about quantum criticality on a compressible lattice. Essentially, we are interested in the physics of quantum critical systems when they are coupled to non-rigid lattice degrees of freedom, that is basically the phonons. Okay. Okay, now I can't change this. Yeah, no, nothing is working. Just a minute. Okay. Okay, good. Okay, so before going to the main part of the talk, I would like to mention that this is based on a recent paper of ours, which is submitted to PRB now. And I would like to acknowledge my collaborators, Professor Marcus Lars, Franke, who is a PhD student with Marcus, and Nicholas, who was a master student in his group. And this work was done basically when I was a postdoc in KIT, Germany. Okay, and okay, I would like to acknowledge German Federal Research Foundation for this project. Okay, so here is a brief outline of my talk. Okay, if I'm moving away, I don't know. So I will start, as I will talk a lot about classical or quantum criticality. I will start with a basic example and define what I mean by classical and quantum phase transition. I'm pretty sure all of us know about this, but just for the completeness. And then I will talk about what can happen when a classical critical system is coupled to elastic degrees of freedom of lattice, that is phonons. And based on these findings, and motivated by these results of these findings, we ask in our work what happens if a quantum critical system is coupled to elastic lattice degrees of freedom, and which is basically the objective of our work, of this current work. And in this work, we took a specific example, which is a quantum critical 5-4 theory, which is coupled to now the lattice degrees of freedom, that is phonons. And we try to see what is happening for such a systems. Today, I will give you some key results for this system. Key results, basically, of our findings for these systems. And then I will give you a brief summary of our work. Okay. So, sorry. Okay. So this is a phase diagram of a rare earth insulator, lithium holmium fluoride, which has basically effective spin degrees of freedom, which are Ising-like. That means they can only point up or down. And now, if we see this phase diagram, this is the y-axis is temperature, and the x-axis is basically some transverse magnetic field. What we see is that for this material, the ground state at t equal to 0 is a fully polarized ferromagnet. That is, all the spins are either up or down. Now, if you turn on the temperatures, the ferromagnetic spins basically get disordered due to the thermal fluctuations. And as you increase the temperature at some critical temperatures, which is Tc, due to this thermal fluctuation, half of the spin gets flipped, and eventually this ferromagnetic moment gets destroyed, and the system becomes a paramagnetic. That is, there is no net magnetic moment. Okay, so this transition here is a second order classical continuous phase transition, and it is governed by purely the thermal fluctuations in the systems. And this point, Tc, where the phase transition occurs is basically we refer to as to this point as classical critical point. Okay, now more interestingly, for this material, there is another kind of phase transition that they can exhibit. So it has been found experimentally that if we are at t equals t equals 0, and if we turn on a different tuning parameter, for example, a transverse magnetic field, this ferromagnetic ground state actually can evolve to a quantum paramagnetic state, and this is governed by the quantum fluctuations that are present at t equal to 0, and which is basically demanded by the Heisenberg's uncertainty principle. So, and this phase transitions at t equal to 0 is basically a second order continuous quantum phase transition, and this point is known as the quantum critical point where the phase transition occurs. Okay, so now one might wonder why we are interested at t equal to 0 phase transition, because this is not physically accessible. But interestingly, there are lots of condensed matter materials where it has been found that if one considers the presence of such a quantum critical point in those materials, one can actually explain various anomalous high temperature properties, physical properties of these materials, and especially in this quantum critical regime. So to give you some instances.
Just to be clear, this would be an XY transition.
Yes.
In that universal.
Yeah, exactly. That's right. Thanks. To give you some instances, so here I give some experimental data. So for example, this is a heavy fermionic systems where we see a phase diagram. Y-axis is temperature and the x-axis is basically magnetic field. And here it is temperature again. This is for iron-based superconducting materials, and the x-axis is doping, which is different from temperature. So for both of these systems, there is one assumes that there are quantum critical points present, and in this regime, these materials exhibit non-Fermi liquid behavior, which is basically the resistivity in this regime goes linearly with temperature. And one can actually explain this quite exotic anomalous properties of these materials if one considers the presence of quantum critical point in this material. This is another example. This is another heavy fermionic system where it has been found that there is an emergent superconductivity close to this quantum critical point. That is, one can explain, or the existence of this superconducting phase actually relies if you consider a quantum critical point in these materials. And so far in this system, the only degrees of freedom that are acting is basically the electronic quantum critical degrees of freedom, and lattice does not play any role. So there is no role of phonon in explaining at least these properties. Okay, now we turn to our topic basically. So we are interested when this classical critical systems or quantum critical systems are coupled to say elastic lattice degrees of freedom or phonons. So this was basically considered in a pioneering work by Larkin and Pekin in 1969, where they considered coupling between classical critical system and elastic lattice. So let's see what they considered. So for classical critical systems which exhibit a second order continuous phase transition, and here is the Lagrangian for such a system, and psi is basically the order parameter of the critical mode, and here A, this constant is proportional to proportional to T minus Tc, where T is temperature and Tc is basically the temperature where the phase transition occurs, and B has to be greater than 0. And these systems exhibit a second order transition when A becomes 0, and at this transition one can show that the specific heat, which is proportional to this psi square average, actually diverges near the critical region. Now they considered what happens when they couple these systems to the elastic lattice. So basically what they consider is like an interaction Lagrangian of this form, where the energy density, which is proportional to the psi square, is coupled linearly to the strain tensor of the systems, and lambda is basically the coupling constant.
Sorry, one person.
Yeah.
How you choose the strain? I mean, is on axial strain? Is any specific strain?
So okay, yeah. So for this is a volumetric strain. So basically, if you consider strain tensor, it's the trace of that.
Okay, the
yeah,
trace.
yeah, yeah, exactly. But you can.
And why is this the natural coupling to consider?
Why?
Why is it natural to consider coupling it with psi squared rather than secondary coupling to psi itself?
Yeah. So this is dictated by the symmetry of the system. So for I think a magnetic system you can have psi, but this is if you consider the symmetry of this system, this is the lowest order correction.
This is the inversion as inversion symmetry.
Yes, exactly. Due to the inversion symmetry. Yeah. So yeah, exactly.
But why does the strain respect that? So why does this?
This is a volumetric strain, so it does not break. Yeah, exactly. Yeah. Okay, so remarkably, they were able to show that if you consider this Lagrangian, it actually instead of this system, instead of a second order continuous transition, exhibits a discontinuous first order transition. The analysis is quite involved, and of course, this is beyond the scope of today's talk. But I will give you a glimpse of the working mechanism.
So how are they treating the epsilon? Are you treating it as a constant volumetric?
No, this will appear as a field. So I will show you. Yeah, exactly. Yeah, so this is basically the next slide. Okay, so this is the total action of the systems, where of course, so these are the three parts. The critical system, as I described, is given by this Lagrangian here. The elastic system is the Lagrangian for the elastic system is this. So now you see that the strain is basically the derivative of the atomic displacement field, and it enters the Lagrangian. And the interaction is the volumetric strain, as I mentioned. So it's basically in there. Okay, so the approach was quite intriguing. I'm sorry. Yeah, the approach that Larkin-Picking took is basically to integrate out the elastic degrees of freedom. Now they could do it because of the fact that these elastic degrees of freedom actually appear quadratically in the Lagrangian. So you can integrate out this and get an effective action in terms of just the psi fields, that is the critical modes of the system. So basically you start from the partition function where you have both this strain field and the critical field, and then you integrate out this U field and you arrive at this effective action. The resulting action is given by this equation here, where we see.
Can you go back one slide?
Yeah, sure.
So yeah, it's just a quadratic formula.
Yes, exactly. And well, I mean, this I did not mention, but these are basically bulk modulus and shear modulus of the piston.
The story, I don't know much about it.
Yeah, sure.
Does it mean that this African film you consider them non-propagated,
Here, no, this is only the potential. But well, for our system, we'll see we have a kinetic term when we are considering a t equals 0. Yeah.
It's equivalent to
Oh, it is equivalent. Yeah. Okay. Are there any questions? Okay. Maybe I can then move. Okay. Oops. What? Sorry. What?
In marginal quantum theory, people interested in have you ever done that
I'm sorry.
if I'm integrating out of the then other theories have you done
Okay, the mass, yes, actually, eventually, I mean, it's not fully done here, but the mass term, like A also gets modified.
But I'm saying this fluctuation are massive, right? So we can get it out.
Yes.
So the why we're massless,
Oh, okay. No. So these phonons are massless. That's why, I mean, I'm going to say this.
It's not low.
Yeah, exactly. So
Okay,
yeah, these are yeah. So that was the tricky part of this calculation.
You have evaluated the determinant here,
Yes.
and this is the result of the determinant at the end.
Yeah.
Why did it work out to be this? Just as if you can say 1 or 2 words about how that worked?
Okay, I can give you some intuition. So the phonon fields are massless, and so this non-local term is basically arising due to like q equal to 0 modes. So essentially, if you, for example, if you consider this U field, you can write it in terms of Fourier components, and then there will be like a bulk mode or q equal to 0 component and q non-zero components. So this q equal to 0 components will give rise to this this non-local term basically.
The q equals 0.
Yeah, exactly.
Okay. All right.
Yeah,
Then
exactly.
I see how it works.
Yeah.
It's just tadpole, essentially tadpole diagrams.
Yeah, there are always no local term once you figure it out.
Exactly. Okay, so eventually this term, they showed that, I mean, I am not presenting here, but of course you can, if you're more interested, then you can go to these 2 papers and see the details. This will eventually drive the first order transition in the systems. So basically what they get is like, you know, if you couple this lattice to the classical critical system, this system exhibits a first order transition. Okay. So well, after this work, there were subsequent.
You would have had higher order powers of psi there if you had connected.
Sorry.
You would have had a higher order powers of psi in that expression.
Okay, just let me go back here. You mean?
Yes, I expect that there are higher order powers that are less relevant.
Okay, and why would they be less relevant? Sorry,
I'm not sure, but presumably.
Okay, I mean, I'm not very sure why. Okay.
When your psi squared entered as a term, it came from the epsilon term in your the coupling with the epsilon coupling with, with this. So it's a determinant of psi squared that entered, which is some non-local one, and you can expand that out in diagrams, and there will be more powers of psi.
Okay.
But you have made some argument that suppressing those, I presume.
Okay.
Presumably because you're close to the transition.
Oh yes. Yeah. Okay. Yeah. This I haven't thought about. But okay. Yeah. Okay. Thank you. Yeah.
The orthogonal psi dependence is in this A function.
That is the original.
That is the so this is basically the yeah, exactly. Yeah.
Kind of determinant for integrating out with the this would be the leading term.
It would be in a power expansion of psi, it would be the leading term. She has there's clearly a quadratic term that she has corrected in that S term that Venus mentioned. She's included a correction to that in there. But now if I go to the power of psi squared in this term, but then we've been upside to the 4th term, they would be upside to the 6th term, upside to the 8th term.
Okay.
There's nothing that prevents those from existing there, so they must be there.
Okay, yeah. Okay, thanks. Yeah. Okay, so after this work, there were like subsequent works, I mean more rigorous work like RG analysis, considering this kind of classical critical systems on compressible lattice, and there are a huge body of works, but all of them found like, you know, this system tends to exhibit a first order transitions. Well, this is not just pure theoretical like, you know, questions. It has been actually found in a couple of materials, for example, classical ferromagnets near Curie point, classical ferroelectrics and binary alloys, where these systems exhibit like weak first order transitions because of this kind of coupling in the systems. Okay. The transition temperature actually depends on the, it depends on the boundary condition, I think. Like, for example, the volume that of the material, or how these transitions are occurring, basically. For example, the volume of the physical system, etc. So it might change. Yeah. Okay. So another interesting thing is that later in this paper, it was shown that this first order transition actually can be seen in lattice instability. So let me tell you a little bit about it, and basically we will encounter this kind of argument later in my talk. So as I said, in absence of the coupling to the lattice, this critical systems has like a specific heat divergence near criticality. Now, in presence of this type of coupling, one can actually compute the correction to the elastic modulus of the lattice, which is coming due to this interaction Lagrangian. And if one computes this correction perturbatively in this interaction, one sees that this is sort of proportional to lambda square times the psi square expectation value. Now, as near criticality this quantity diverges, this will also diverge. And if one computes the re-normalized elastic modulus, it essentially becomes negative. So for an unstable solid systems, basically this denotes a structural instability, because for a stable solid systems the elastic modulus has to be a positive quantity. So this actually indicates a first order transition in this system as well. Any questions on this?
But basically with the negative elasticity of
so I mean, so my physical intuition is that for solid, if you apply a strain, the stress is basically along the same direction, so there is no relative sign sort of. So and that is stress over strain is basically sort of the elastic modulus, the ratio. So if it changes sign, that means the solid loses its property, like stability.
It just collapses.
Collapses, exactly. Okay. So what we see is that here, as we saw, this specific heat diverges near criticality, and near criticality it has temperature dependence, which is given by this equation, where alpha is specific heat exponent, and if alpha classical, which is again related to the dimension and the correlation length exponent by this equation, becomes positive, this diverges. But now, in presence of such a coupling to the lattice, this classical critical system will, instead of a second order transition, will exhibit a first order transition. In other words, what we see is that the structural instability for such a coupled system actually implies that alpha classical is greater than 0 or vice versa. So one can have, so if one has alpha classical greater than 0 for such a coupled systems, one can expect the system will exhibit a structural instability instead of a continuous transition. So this was the finding, and in our work we are motivated by this argument, and we sort of ask whether similar things happen for a quantum critical system or not. We want to see if quantum critical systems are coupled to lattice, similar to these classical critical systems, whether we get a structural instability when the alpha quantum, now which is basically modified through this equation for quantum critical system, if it becomes positive, whether we have a structural instability or not, and vice versa. So in our work, we basically testify this condition for a particular quantum critical Kuiper theory that I will now describe. Is the motivation sort of here? So this is, you might think this is again a purely theoretical endeavor. It is at this point, but I will give you one example. For example, these are basically ferroelectric systems, strontium titanate or potassium titanate. But in recent experiments, it has been found that they actually can exhibit a ferroelectric quantum critical point. And for these systems, interestingly, it has also been found that the dielectric constant, for example, of these materials shows some anomalous temperature dependence. And to explain that temperature dependence, one needs to consider such a coupling of lattice and the ferroelectric quantum field. But well, I mean, in our work, the theory does not describe these systems. This is a little bit complicated. So for our work, we simply work with the phi-4 theory. Okay. Anyway, so this is our working model. So we consider a Lorentz invariant phi-4 theory with n component field phi that couples to the acoustic phonons. And well, we are quantum critical system. So at t equal to 0 and we are at d equals 3. And the Lagrangian for this critical systems is given by this equation. Here, okay, okay. Here, well, this is the dynamic part, of course, like the kinetic part, and C is the velocity of the critical mode, R is the tuning parameter of the phase transition, and U is the self-interaction constant. And for us, as it is Lorentz invariant, we have the dynamical exponent for this critical mode to be 1, and these phi fields are basically vector. Well, for this theory, the Beer-Gibbs function is given by this equation here.
You have gotten Euclidean algorithm.
Yes, I do. Yeah, exactly.
Yes, sorry, it's Lorentz invariant because it is quadratic in time.
Yes, exactly.
Because usually we do the criticality without Lorentz invariant.
Yes, yes, you can.
You're assuming that it's Lorentz.
It is Lorentz invariant for, yeah. So it's basically a model system for us. Yeah.
So it could be also the derivative, first derivative in time.
And absolutely.
Okay.
For example, I think in metal.
Yeah,
Yeah,
exactly.
metallic system. Yeah. Okay. Okay, so the Lagrangian density for the elastic lattice or the phonon is now given by this equation. Here you see that we have a dynamic part indeed because we are at t equals 0, and this is basically similar to as we have it earlier. And here CIJKL is elastic constant tensor. And we have considered acoustic phonons, so the dynamical exponent for phonon is also 1, and U is basically that atomic displacement. So, and now for our working purpose, we consider cubic isotropic elastic lattice systems, and dictated by all this symmetry of the systems, the Beer-Gibbs function of this phonon modes becomes this, where CS is basically the longitudinal sound velocity or velocity for phonon, and CS is given by this equation where K is the bulk modulus and mu is the shear modulus. And we again consider interacting Lagrangian between the quantum critical modes and the strain, which is given in this equation, which is very similar to what we saw before. Lambda is elastic coupling constant and phi is the critical modes, and again we basically couple phi square linearly to the volumetric strain. So, so the ON symmetry is also preserved due to this interaction. So no symmetry is broken. Any question?
Could you choose a volumetric strain that is constant? I mean, it's sort of unimodular strain such that the volume element is always constant. So I'm not saying that the constant is strain, but once you calculate the volume element, it becomes constant. It's a very special kind of choice. Also in gravity, it's something that the metric, the determinant metric equal unimodular gravity. Could you have for instance, special choice? Because this is the couple completely right the strain to the field, right? To the field square.
Yeah, I mean, I think nothing is stopping you from doing this, but at least.
No, I was just wondering, if something happens specifically when we pick up this, specific kind of strain where the volume element is just constant. It's like incompressibility. If you have a fluid and you try to incompressible fluid is a uniform fluid, but the area of the fluid is remains constant.
Oh, okay, yeah, I see. Yeah, so this kind of boundary conditions. I mean, yeah, you can have it. I mean,
well, it would be constant. Sorry.
Where do you see the change chosen?
Well, she has the volumetric strain, no? So
Well, you got down to the bottom line.
yeah, there is a volume element of the strain. It's it's a symmetric tensor, so like look like a metric-like object.
Yes, it's a
Principle, what is think what happens if you know, I take a unimodular metric, unimodular strain, and which is usually is for incompressibility, something that you want to do. At least for fluid, not for
okay, yeah.
model.
Okay.
Just a curiosity, just
yeah, for
the formalism is quite general.
Yeah.
She didn't really need to state that she had chosen a particular lattice area, but you could have done this for any lattice.
Absolutely. I mean, there are lots of work, like, you know, for the classical system where they consider various symmetry and like,
it's
you know.
not really necessarily a lattice, it could be any fluid, but you take a continuum.
Yes, exactly. Yeah. So, but the results might differ because then this mu goes to 0 for fluid. So for solid, this mu is like always.
You will see a lot there.
Well, yeah. I mean, I'm just saying, like, you know, for macroscopic stability, this might be the results might be a little bit different, but you can of course consider. Yeah. Okay. Any other questions? If not. Yeah, so basically this is the action for our systems. Well, yeah, and this is the total Lagrangian. Now, what we see is that if we do a simple scaling analysis, what we see is that both the self-interaction U and this elastic coupling, they are marginal in d equals 3 with respect to the Gaussian fixed point. So this actually tells you that a proper way to deal this or to analyze this system is basically doing a re-normalization group treatment. So we, in our work, we indeed perform one loop perturbative RG and yeah, to analyze these systems. Okay.
You argue that the index of U is not just a vector. The index of U, is that just a vector?
U is a vector. Yeah.
There's different types of motor forms.
Yeah, so basically because, yeah, exactly, you can have transverse mode as well, but because of this interacting Lagrangian, where it is coupled to the energy density through this trend, this transverse part actually, it can be shown that it doesn't play a role, so only thing...
Focusing on the
exactly, yeah. Yeah, but in general, there can be a transverse mode. Okay. Yeah. Yeah.
You have a U point before, that's a different U, isn't it? You're not forcing that.
Sorry, can you...
You have a U times twice the force, which was always a different U.
Oh yeah, sorry about that. Yeah, so this is a little bit, you know, this is, I'm being sloppy about the, so this is displacement field, you know, and this is basically the coupling constant for the 5-4 term. You can, yeah, absolutely, yeah. This is different from this U. Sorry about this, yeah. Yeah, maybe I should read it.
Tell us the gradient of U of the vector.
Mm-hmm.
Then E that U is the trace of it.
Absolutely. Mm-hmm. Yeah, exactly. Okay. Mm-hmm. Okay, good. So, okay, so basically we need to compute the one loop corrections to the propagators. So here are the diagrams that are contributing for the critical mode propagators, and here is the self-energy correction. For the phonon modes, okay, only this diagram is contributing here at one loop level, and this is the self-energy correction for the phonon. And okay, to compute this loop integrals, one need to regularize it. And for, as we are considering condensed matter system, and we have a natural length scale cutoff, which is the lattice distance, we basically put a hard cutoff to compute this integrals here. So lambda is basically the ultraviolet cutoff. And there's a little bit of change in the convention. So here CL, I will actually later use CS as the sound velocity, which is basically the same sound velocity. Okay, next we compute the one loop correction for the vertices. So for the U vertices, these are the diagrams that are contributing, and here are the corrections. And for the elastic vertex, these are the diagrams that are contributing, and here is again the correction. Okay, now once we have these corrections, we can basically construct our RG equations once we integrate the momentum modes between this momentum shell, where b is greater than 1, and we eventually arrive at this RG equations here, where L is basically logarithm of b, which is the RG scale. Okay, so what we say is that due to this coupling, both the velocity for the critical mode and the sound velocity also flows, and of course we have the flow in the mass, the self interaction, and the coupling, elastic coupling constant. Next, what we do for like a simpler presentation, we considered this quantities instead of this one.
Can you just go back to your propagators again?
Yeah, sure. Propagators, okay. Mm-hmm.
Yeah, so the I is treated as relativistically invariant, and the elasticity is not. It has different propagators of the mode. It looks almost similar, just that it has a different velocity of sound.
Sorry, could you repeat your question?
It's also treated as with different velocity. Your dij, your elasticity of field. Oh, it's Q. It's got a Q squared.
Yeah, exactly. Yeah. Okay. Okay.
That's presumably times delta by j. There's rotation in there.
Yes, it is. This is okay, so we write the RG equations in terms of the ratio of this velocities here, and we basically reparameterize these other quantities, but we keep the R same. What we see is that for all these RG flow equations, we have a solution for R equal to 0 that actually ensures that we can work close to the criticality. Now once we have this RG equation, we can find out the fixed points. We find by solving this equation for 0, and we find two kinds of fixed point. One is the usual Gaussian fixed point, and the other one is the Wilson-Fisher fixed point, which is given by these two values. And we also compute the specific exponent for these coupled systems. What we find is that for Gaussian fixed point, it is epsilon over 2, where epsilon is basically 3 minus d, that is the how far we are away from this three dimension. And but for Wilson-Fisher fixed point, this specific exponent is given by this quantity here. So what we see is that we actually have a situation, not for the Gaussian, but for this Wilson-Fisher fixed point, where if we consider n to be less than 4, we can have alpha quantum greater than 0. And if one has like n greater than 4, you can have alpha quantum to become negative. Now, our interest is basically to see what are the consequences of these two regime, because we, as we said earlier, like, you know, we expect that for this situation that we can have a structural instability, but let's see what actually happens for these two cases. So to do that, n is the component of the 5 4 theory.
It's generalized.
It's n, yeah, it's n component. Yeah, exactly. Yeah, so that's why. Yeah.
So you could treat this more or less exactly in that.
That's a good question. Yeah, that's a good question whether we can do. Yeah. Okay. So first, let's consider the RG flow at d 2.9, which is like for small value of epsilon. We are close to 3 dimension, but not yet there. And n less than 4, that means alpha quantum greater than 0. So here I plot the RG flow in the lambda tilde and u tilde plane. What we observe is that we have a Gaussian fixed point, which is denoted here, and this is unstable both under like this elastic coupling and this self interactions, because the flows are away from this fixed point. Yeah. And what we also say is that we have a Wilson-Fisher fixed point, which is given by this dot here, on this axis, and this is stable only along this u-axis, but once you turn on a little bit of elastic coupling, it's actually unstable and the flow is towards strong coupling. So this actually suggests that the strong coupling or the runaway flow actually suggests a first order transition in the systems. And actually it can be shown that for this, when this lambda tilde is, is diverging, the sound velocity actually vanishes in this entire parameter space. And sound velocity is in turn proportional to the elastic constant of the system. So that means the elastic constant of the system vanishes, which actually indicates a structural instability or first order transitions in the systems. So that is good that at least, I mean, for this quantum critical system also, for alpha quantum greater than 0, we can have a first order transition similar to the classical critical system. And well, the elastic coupling is relevant part of it, as we can see from this flow. And if we go to n equals 4 limit, the elastic coupling becomes marginally relevant with respect to the Wilson-Fisher fixed point. Okay, so next we come to n greater than 4, that is alpha is less than 0. Here the flow is quite intriguing. Let's see what's happening here. So again, we plot it in the lambda tilde and u tilde plane, and what we see is that we again have a Gaussian fixed point which is unstable with respect to the elastic coupling and the self interaction. But now here we have a stable Wilson-Fisher fixed point, but it is below this sort of this dashed orange dashed line, which we refer as separatrix. So you can see that the flow is towards this Wilson-Fisher fixed point below this line, right? But above this line, the flow is again away from this Wilson-Fisher fixed point, that is, it flows towards strong coupling. So what we can infer from this plot is that this, well, first of all, the separatrix basically differentiates between the strong coupling and like weak coupling regime. And we will see in more detail what is actually happening in these two cases, like whether there is a structural transition or not. And also for n, when n goes to 4 in this case, we will see that the slope of this line actually vanishes, and this point basically merges towards this Wilson-Fisher fixed point. And again, the elastic coupling becomes marginally relevant. Okay, so let's now see in little.
You have another strong fixed point. Is that a Gaussian fixed point? It's
No, it's this one you mean, right?
No, the separatrix should connect two fixed points. I see the lower one, the Gaussian fixed point.
Yes.
And the Wilson-Fisher.
Yeah.
But the separatrix from the Wilson-Fisher to the strong coupling fixed point, presumably that's a strong coupling Gaussian fixed point of an infinity.
Well, it is.
One upwards. Yeah,
that will occur at infinity. The strong coupling Gaussian, but this is not a Gaussian.
No, I know, but if I go to the right.
Ah, okay. So
the separatrix off,
yeah.
That's a strong coupling Gaussian fixed point, presumably.
Yeah, probably. Yes. Okay. Yeah. Yes, I think we did mention something. Yeah. Okay.
And you said the slope of this line depends on the value of n?
Yeah, because I haven't shown it here, but it if you consider a particular parameter range, like the CS over C is very small, then the slope is sort of like n minus 4 over n. So if it is the n is close to 4, this line basically goes towards this axis, x-axis.
So if your n is less than 4, you always have a first order transition with the massive value of n.
Yeah.
Whereas if it is above 4,
yeah, then we will see like what's happening in this region, because these two flows are quite different here. Okay. Okay, so this plots are not that great. Okay, let's say what is happening in this regime and in this regime. So to see that, let's for now let's imagine we are here above the separatrix and we plot the sound velocity CS. It's quite not clear, but the blue curve basically gives you the sound velocity, and we plot it with the RG scale, and the orange line is basically the elastic constant. So what we see is that in this regime, the sound velocity actually vanishes after finite RG scale. So this goes to 0, but the elastic coupling remains finite. So what we see is that the sound velocity vanishes, and this indeed again basically dictates that there is a lattice instability in this regime of the parameter. But below the separatrix, for example, we are here, what we see, we again plot the sound velocity and the lambda, the elastic constant, with L, like the RG scale. And what we see is that the lambda actually goes to 0 asymptotically. So basically we have a stable Wilson-Fisher fixed point here, and that's why the lambda flows towards 0. But the sound velocity remains finite. So in this regime, there is no lattice instability or first order transition, as it remains finite for a sufficiently large RG scale. So that's quite different from the n greater than 4 case, basically. Okay, I will skip this one because it's a little bit more detailed, and I will come to the d equals 3 dimension, which is actually like the physical dimension or the upper critical dimension of the theory, and this corresponds to the case where alpha quantum is exactly equals to 0. And here in this case also you can consider two different cases where n greater than 4. And let's see what happens for this case. So this is the RG flow for alpha quantum exactly equals to 0 but n greater than 4. What we see is that we have an unstable Gaussian fixed point because the flow is away from this point here, both along u and lambda axis. And if you see closely, this separatrix which we saw earlier, it exists, and you still have this stable Wilson-Fisher fixed point, but now in this case, the Wilson-Fisher fixed point actually moves towards this Gaussian point, basically margin. So all the flow, it looks like it's going there. And above this regime, the flow is again towards strong elastic coupling. So it goes in there, but then it diverges if you're closer to the Gaussian or the Wilson-Fisher point here. And you can basically calculate or find out the value of this lambda, for which, like the critical value of the lambda, above which we'll have a runaway flow. And next you can consider this case where n is less than or equals 4 and greater than 1. For this we have basically a structural transitions as we saw in the first case, basically for entire parameter space. Okay, with this I will basically conclude and give you the summary. So what we saw is that, well, for our case, structural instability occurs for this compressible quantum critical system described by FIFO theory. We have for alpha quantum greater than 0 a quantum structural transition for any finite value of lambda, as we saw. So this is kind of shown in this plot here. So here, if alpha quantum is positive, we have structural transition for any value of lambda, any finite value of lambda. But for alpha quantum less than 0, we have a Wilson-Fisher behavior here, and above a threshold value of lambda, that is, above the separatrix that we saw earlier, there is a structural transition again, which is quite different from the classical critical system, I guess. And for d equals 3, exactly 3, I think both of the couplings are marginal and the flow are logarithmic, but one observes like the similar behavior which is reminiscent to this 2.99 dimension. Yeah, with that, I would like to basically conclude. Yeah, and just a side comment for n equals 3, it actually describes a quantum insulating anti-ferromagnet thallium copper chloride to give you some some physical system which is described by this n equals 3 FIFO theory. But well, I mean, here no structural transition has been observed so far, so this is just a pure theoretical. With that, I would like to thank you for your attention.
Questions?
Yeah.
So is it always true that inversion symmetry remains unbroken for any values of interaction? Or you see certain region in the parameter space in which a certain point of inversion could be broken? This interaction could break coupling with
Yeah.
strength to break some crystalline signal. In this case, inversion, right, is the main signal.
In this case, no. No.
But you choose Landau's book theory that respect inversion signal.
Yes. Yeah. Yeah.
So it remains always unbroken.
Yeah. Exactly.
Okay.
Yeah. Yeah.
So in this case, you don't have any.
That's certainly not true. It's not really true.
It's possible
Because she's dealing with her n equals 1 case is Ising.
Yeah.
And if you go to below the Ising transition, that inversion symmetry is broken.
Yeah.
Because there's a magnetization.
Sorry, for n equals 1?
N equals 1, yeah. The Ising system.
Yeah, yeah, okay.
Below the transition, below the Ising transition,
okay.
you have magnetization, which breaks that C2 symmetry.
Yeah, yeah, I
So
get it.
it's a good question what it does, why you can still neglect.
Yeah, because usually by breaking a crystalline signal, you get a new phase transition, basically.
Yes, yes, yes.
This has been done a lot for topology of system with the crystalline symmetry. Once you break a crystalline symmetry for any reason, disorder or interaction, then you go through eventually a phase transition. I mean, even without topology, then again, I mean, in principle, one could think if there is any distribution from which.
You might expect other theorems to enter, like
yeah, no.
Right. The volumetric one.
Yeah, in principle, even in the.
But
you could have other epsilon dependence on pi in the system.
But you know, when you're mentioning about this n equals 1 Ising transitions, are you like talking solely about this critical system or coupled to the lattice? Because this
lattice,
okay.
The critical system is very well understood.
Yes, exactly. Yeah.
I'm talking about coupling your system coupled to these phonons.
And
that system has you insisted on a pi squared or psi squared epsilon trace epsilon. That trace epsilon squared or trace epsilon. That trace epsilon times pi squared. You could have had terms that involved linear in pi as well because you've broken that C2 symmetry.
Okay, I could take that interaction. That or you're saying.
I think when Tantamini goes one year that something else can happen. And I'm just observing that below the Ising transition, you have that magnetization. The Z2 symmetry is no longer present.
Okay, yeah.
Sarkar was also mentioned with energy density somehow.
Yes.
I think one of the slides Sarkar was.
It's the energy density, yes, of the Ising system.
This thing coupled with the energy density and happens to be.
The motivation she mentioned that it was the Z2 symmetry that was being observed preventing those ones. Maybe you can go around arguments, yes.
Yeah, I need to think about it.
When it is a collapse or there is, let's say, merging or melting of a crystal, eventually you lose a crystal in symmetry.
Absolutely, I agree. Yeah, exactly. Yeah, I understand.
So I would assume that this inversion symmetry somehow broke down. We are breaking a lattice.
Yeah. Okay.
So it could be a way to understand this.
Yes. Yeah, no, I get that.
I think the same way of saying it is you are approaching your study of the system from the symmetric phase.
Yeah, absolutely. Non-condensed phase, yeah, exactly.
And you are tracking just along the zero temperature line.
Absolutely. Yeah. Okay.
So now we have the calculations of the zero temperature.
It is.
Presumably phonons become more important as temperature.
Sorry, what?
Presumably phonons become more important.
Yeah, exactly. Yeah. So that's probably reflecting.
You normally expect phonons to be coupled.
Yeah.
And you also have Maxwell frequencies.
Yes, yeah. That we consider.
Your original system that you mentioned had a rather nice transition crossover from an Ising system to an XY system. You didn't try to treat something along those lines.
I mean, yeah, not in this work, but yeah, that's a good question actually. Yeah, maybe, yeah. Let me think about this question.
But in your code, it would be the any of these two pairs in the tracky along that.
Yeah. Well, I mean, in a way, like, implicitly it is covered, but yeah, not explicitly, like,
So would you do this behavior if we had a non-zero temperature?
This non-zero temperature, what?
Like this is possible to this how to use this model?
Well, I mean, some of the stories are lost because, as I showed earlier, like, for T not equals 0, you mean the classical critical system sort of. And so what we still have for that T not equals 0 is this regime, like, well, I mean, in this regime, we still have the structural transitions, but here for finite temperature, at least there is no structural transition as we have it here. So everything will be Wilson-Fisher like for T not equals 0. Yeah, but yeah, exactly. That would be my naive guess. Any other?
The way you describe this in theory is two types of freedom in the same theory.
Yeah, absolutely.
Presumably, if you choose the parameters in this sort of way, you can separate the states of insulation. I'm wondering whether putting the parameters probably might be able to get a delivery and have some kind of quantum magnet contribution data passing probably the field and stuff.
Yeah.
Effective description for the story.
Yeah.
But this might perhaps help to clarify how to do it.
Yeah, I guess so. Yeah. Yeah, we have to do it.
I think also your large N vector model is probably equal to an exact tree.
Absolutely. I think that those are sort of yeah, it's definitely interesting to see that in here. Yeah, I mean, there are a couple of things like what happens when you, well, this is a epsilon first order epsilon expansion, so we can have like higher order epsilon expansion as well. So I think the fixed point structures might be different, but I would hope that the RG flow will be topologically the same. So yeah, there are things.
May I ask what kind of tools you calculate?
Oh, I use simple Python script. Like to plot this flow? Yes, Python.
You write the code yourself.
What's the question?
What tools do you use to calculate the dynamics of the system?
Like the RG flow, I think she meant. This diagram, right?
She means calculating not plotting.
You mean?
No, not about the calculation. Yeah.
Oh, okay. I mean, it was purely analytical.
Purely analytical.
Yes, yeah.
Yeah, because we do exactly the same thing in early university technology.
Yeah, I mean, it can be hard to handle the complicated equations, but well, we are fortunate, I think, at least for this case, to be able to deal with analytics.
I mean, it's probably also interesting to look at the first order derivatives. I mean, you have a conserved order parameter. In the case you consider there's a conserved order parameter, and z is equal to 1, and given the relativistic system. For many of those systems you're interested in, not in conserved order parameter.
Yeah.
So it would probably be interesting to look at what happens in rather z, rather n.
Yes. I mean, this is really sort of like, I don't think a lot of people work around like, this coupling, but yeah, no, this is probably one of the earlier, what I would say, a lot of things can be explored.
We can thank our speakers again.
Thank you very much. Okay. Okay.